My goals here are to connect this concept in statistics back to something you learned in algebra, to show you how to do this on a TI-84, and how to do this in Desmos. But if you are here quickly for where are the buttons in a TI-84, it is second vars 2. And it will lead you to this menu right here. So that is the quick answer to it, but I will explain a whole lot more as we go along. You need to find the area between these two z-scores. All right, I want you to take this back to an algebra class when you had to do interval notation, and it's the same idea. So I'm gonna take away all the stuff that we don't need to talk about right now. It's all, all this stuff is gone, delete. And then we're really just working with, let's say, something like, that's too big, something like, okay, there's our x-axis right there. Okay, and then you had this point right here, and you'd have this point right here, and then it's your job to use the, to find, the shaded region, and then you have to write this in interval notation, and you'd be like, okay, well that's negative 2.5, and it goes all the way to 0.9, and you'd be like, that's my interval notation because this would be the thing on the left, and this would be the thing on the right. It's the same thing from when you were in algebra. Let me elaborate. I mean, we're really just going from an x horizontal axis like we had before in an algebra class, using interval notation and all that business, to a z being the horizontal axis with a normal curve over it. So anyway, here's what we're going to do with that. We're going to go second and vars. So we want this distribution menu. We're going to use normal CDF because the C stands for cumulative, so add up all the areas between here and here. Now, on the left, that would be our negative 2.5. Then that's going to be our lower bound. So negative 2.5 is going to be over here. And our upper bound is going to be 0.9. This is exactly the same thing as your interval notation from left to right. Lower to upper is the same as that left to right system for your interval notation. Now, because we've switched from x's to z's, that is why you're going to leave the mu alone. Let the mu be 0 and let the sigma be 1. So your mean is 0, your standard deviation is 1. Leave it alone. And then if you have Stat Wizard on, you have this menu right here so that you can have this really nice little interface. And the reason why is that when you hit paste, it's going to come onto your home screen. So right here, you'll see your interval notation. Well, it's the stuff that your interval notation gives you. And then this is going to tell you what your mean is, and this is going to tell you what your standard deviation is, but we're dealing with z's, so leave those alone. So normal CDF from here to there would be that. So what I want you to do when you see something like this is I want you to imagine the shaded region that is right here. That's the goal. This is overlay your algebra studies on top of your statistics studies. So, and I mean, it's accurate. The thing in the bottom left corner is accurate because we can go from, let's see, 5, 0.9. The thing I want to address really quickly is just like, how can something, just a horizontal shading, be the same thing as this bumpy thing? And it's that's already kind of calculated in there. So I mean, this is what's happening right there. This is the stuff that's happening behind the scenes. But the fact that it's the normal CDF is taking all of this nonsense that you have no need to know right now into account. So the fact that it is from here to here is taking care of the fact that it's, sometimes it's the high bumpy part right here, and sometimes it's not the high bumpy part. It's fine. It'll figure that out because where the numbers are here. But you just have to specify this interval. And so the same way you learned interval notation when you were in algebra class, you're going to overlay that on top of this idea right now. But that's what it's doing. That's how it's figuring out what the probability is, because underneath, as long as it's a z and not x's anymore, then underneath this is going to be an area of 1. And that means that an area of 1 is the same thing as 100%. And therefore, whatever area you're defining is a percentage, and that's going to give you your probability. But you see how right here, there's less blue area than, let's say, that. There's more blue area, even though this lateral distance right here was the same as that, then this area is less than that. It's using where those numbers are in that interval and figuring out under that curve how much area is there. Well, what about this one when you don't see something on the left? It's just kind of going to the left, and we're looking for something that's less than a particular z-score. Well, if you're going to draw your, if you're going to draw your horizontal axis here, and you have this right here at negative 1.2, then your shaded region would be over there, right? Well, that would be the same thing as saying that your interval is from negative infinity all the way over to negative 1.2. There we go. How do we say that in a calculator? This is that way, and then this is that value right there. We'll go to the distribution menu, which is second and vars, number 2 for normal CDF. So right here, remember that we need a number. It's a calculator. It's a machine. It can't have the idea of negative infinity in there. It needs a number. So this just means negative 1 times 10 to the 99th power. So negative 1, 0, 0, 0, 0, 0. Really, 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 really negative number. So something like this would work. I could type in a negative 7, and that would be sufficient. Sometimes we type in a negative 10,000, but just, negative a lot. And so this right here is the idea of a negative infinity without actually assigning the idea, instead of assigning a number that's really, really, really astronomically far down there. My upper bound is going to be that negative 1.2. Leave all the other stuff alone. And only 11.5% of that data is between negative infinity and negative 1.2. So there's that 11.5% again. But I wanted to show you that you can also find this on Desmos. So you're going to pull up this keyboard and go to Functions, Normal Distribution. Not where I wanted that. So 0 and 1 to tell it that we're really dealing with z. And cumulative probability, you have to give it your lower and upper bounds. We're going to give it a negative 100's enough, just negative stuff. The idea of negative infinity, but really, you don't have to go real far with that. And negative 1.2. And there's that 1.5. It's the long answer. And let's make it a different color. Let's make all this purple. Yeah. So it will find it for you here too. What if they want you to find the area that's more than a particular z-score? So we are over here remembering our algebra class. There's the dot right there. The shaded region is this direction. Positive infinity is over here. So my interval is going to be negative 0.7 all the way to infinity. The last one we did was a little piece of it. It was on the left, a little chunk, and only 0.115. It was only 11.5% of the graph because it didn't even cross over the halfway mark. It didn't even get to the bumpy part. But now we are clearly past that bumpy part. So we should be expecting at least 0.5. We should be expecting, in fact, more than 0.5, because from the mean all the way to the right is going to be half of the stuff. Is going to be 0.5 of the stuff, and we have more than that. So second vars 2, and I'm going to go this time from negative not 0.07, but negative 0.7, all the way to, and I need some number that means a whole lot. So as long as it's bigger than, 6 or something, we're good. Technically bigger than 4, but, I'm going to put 100 in there. There we go. More than halfway. Does it look like about 3/4 of the stuff? Yeah. And just a note on accuracy here. I went back and put a bigger number in there as my upper bound, because remember it's trying to go to positive infinity, and I didn't change anything in here. Here is the calculation with an integral. Here is the calculation with the normal distribution. Move this around so you can see it. There we go. Here's the calculation with the normal distribution. Accuracy right there. So just a note on the accuracy of that. But that's all good enough for, 6 of one dozen the other as soon as you are rounding to 4 decimal places anyway. So you have more accuracy than you need. And it's certainly much more accurate than the tables, because the tables truncate real fast. Big fan of using a machine to do this normal distribution instead of a table.